get into talking about Lewis diagrams and the Vesper shapes, I want to clarify the difference between the ionic bonds that we talked about in chapter 6 and things like the lattice energy and the strength of those bonds, and the covalent bonds that we've been talking about, like the bond association energies, which is different when we talk about the ionic versus covalent. Everything that we've done with ionic versus covalent has clearly differentiated those two, and the way we differentiated them is to say for ionic bonding there was this transfer of electrons from one atom to another. For the covalent bonding, it was this sharing of electrons between two atoms. So what actually happens, even though we separate them for a lot of what we do, is there's this sort of range. So it's not necessarily that things are covalent or ionic. There's different categories of covalent. And even when you get over here to ionic, there's bonds that are more and more polar. So more and more ionic in character or polarized based on one having a more positive and one having a more negative charge. I put these particular combination of atoms together and I put them in a particular order. So how did I put them in order? So how did I figure out, instead of just these are examples of what's in these different regions, but the order that I put them in was specifically the difference between the two in electronegativity values. Electronegativity values are just for a particular atom. There's an ability of that atom to attract the shared electrons. So the shared electrons are the ones in the bond. And I know we say transfer, but they are in between the bonds. So the difference in those electronegativity values tell us how polar or more ionic they are. It would be good to go back and read over this part of the book. So for all the way over here in this category, if I knew the electronegativity values, or even if I didn't know the electronegativity values of hydrogen, I know that the difference, and they're the same electronegativity value, the difference in them is 0. And I'm going to put 0.0 because you'll see why in a second. So there's no electronegativity difference. That's why we call them non-polar, is it's not polarized where one atom is taking or attracting the electrons more than the other. Then if we get to the carbon-hydrogen bond, so the difference between those two, and really quick, let's zoom in. So if we zoom in, and I won't keep doing this, but if you wanted to go back, this is in one of the slides, and you could print this out and go through this video again. There's these little values that are under each one of these elements. That's its relative electronegativity value. So when I go through and put numbers above each one of these so you could see the range, what I'm doing is taking those values for each one of the atoms and finding the difference in them. So if I went over there and I got the value for carbon, and I got the value for hydrogen, and I subtracted them, I would get a value of 0.4, which is why it's good to print that out so you can see where I'm getting these numbers from. Then if I did the carbon-nitrogen one, let me just write up, so I calculated these before, 0.5, the carbon-oxygen one. So I'm just taking the values for each one of these individual atoms, and I'm subtracting them. And see how the numbers are going up. So these numbers, and I'm just going to put electronegativity as En, difference. So as you see, the larger the electronegativity difference, the larger the difference between one atom having the ability to attract the shared electrons more than the other ones is our spectrum from being completely nonpolar, non-polarized in charge, to being ionic. They put values in here, so the values they put in are, they'll put in a value, and this is different. If you look on different books and different sites, it's different. So they'll put a value in as 0.4. Let me write cutoff so you know later on when you look at that. That's the cutoff to say that something's nonpolar. There's a value here, so it's not like truly nonpolar. There's a little polarization, but it acts like nonpolar bonds would act chemically or empirically if you use, instrumentation in the lab. The cutoff here is 2.0. So these cutoffs are telling you if something's covalent or ionic, if it's polar covalent or nonpolar covalent. And there's different chemical properties associated and physical properties associated with each one of these, like the boiling point or melting point. So as you go through, there is an increase in electronegativity. As you go from left to right, there's an increase in polarity. So the bond is more polarized. We've talked about bond strength. So there's an increase in bond strength. And there's other things that we'll talk about later that are an increase that you can look up in the book, but these are all related to each other. And now we'll be able to think about these when we talk about certain types of bonding.